Hi class, welcome to section 1.6 of our pre-calculus textbook. We are going to talk today about the complex number system. Okay, so complex numbers really just extend our idea of the real number system. It's really in addition to our number system. So the number system that we actually use all the time is a complex number system. So now is the appropriate time to sort of do a review of our complex numbers. So we cannot square a negative number. That's where the idea of what's called an imaginary number comes from. The square root of -1 doesn't exist, right? There's no way that we can take the square root, that we can find a single number that when we multiply it times itself gives us a negative, right? Positive times a positive is positive, a negative times a negative is also positive. There's no way to take the square root of a negative, which means that we're really leaving out a complete half of our number system, right? Basically all of the negative numbers now we can't take a square root of. So we have a definition that helps us with that, which is the imaginary number I is the square root of -1, okay? So that means that if you take I times I, you're basically taking the square root of -1 times itself, which we know would basically put it as -1 times -1 under a square root, which will give us -1. Okay, so a quick note here is that remember the property is that if you have the square root of two things inside of a square root sign or a radical sign, it's the same thing as separating those two items into two separate factors, right? However, the square root of -1 times the square root of -1, it is the same as the square root of -1 times -1, but we cannot simplify the -1 times -1 inside of the square root symbol, okay? So those two -1s come out as a single -1, right? So if I want to find the I cubed term, the easiest way to think about that is us breaking down I cubed into two different factors, I squared and I. Okay, what do we have for I squared? -1. And what do we have for I? The square root of -1. However, whenever we see the square root of -1, we never actually write square root -1. We always write I. So what I'm going to get here is basically -1 times I. I'm going to simplify this root in terms of just a single power of I. So I cubed is actually -I. So I to the fourth we can then break down into previous powers I have as well. We can write this as I times I cubed, or a better way, as I squared times I squared. Okay, which will give us -1 times -1, or +1. Okay. So far we have I squared is -1, I cubed is I to the fourth is 1. I to the 5 we can then break down as I cubed times I squared if I want, okay? Or even easier, how about I times I4? So that's going to give me 1 times I, or just I to the 6th, I can write as I times 5, okay, which is a little weird. That'll give me I times I, which is the same as I squared, or I can think of this as any other combination of these things, okay, like I to the 4th, which is 1, times I squared, which is -1, which is -1, so forth and so forth. So let's look and see if we notice a pattern. I to the first power is just I squared is -1, I cubed is I to the fourth is 1, and then I have I again, and then I have -1 again. I to the 7th would be I to the 8th would be 1, I to the 9th would be I. So it repeats. Every 4 powers, the cycle repeats itself. Okay? We call this cyclic. right? It's cyclic mod 4. So we say that the powers of I are cyclic, right? We can define the values of powers of I by dividing by 4 and looking at the remainder. Okay, so for instance, if I want to know what I to the 12th is, I would divide 12 by 4, and its remainder would tell me whether or not I'm looking at I, which is a remainder of 1, I squared, which is when I have a remainder of 2, I cubed, which is when I have a remainder of 3, or I4, which is when I have a remainder of 0. So let's go ahead and look at an example. Let's go ahead and find I to the 26th. So we want to simplify this into a single value of I with either a negative or a positive value. Okay, so what we're going to do is we're going to take 26 and we are going to divide it by 4, right? So 26 goes into 4. 4 goes into 26 evenly 4 times with a remainder of 2. Okay, so it goes into evenly 6 times with a remainder of 2. So I to the 26th is really the same as I squared. Okay, that is our remainder. That's our indicator for which power of I am looking for. Between the 1, 2, 3, 4, we count as 0 because the remainder of 4 would mean I go in evenly, right? So 0 is the same as the remainder of 4. So I to the 26th is the same as I squared, which is -1. So we really only have to remember 4 values. Well, I is easy. It's its own thing. I squared, you guys should be pretty familiar with that from previous experience. I cubed will be -I, and I to the 4 will be 1. You can always think of I4 as, or I to the 0 remainder, as just -1 times -1, right? So it's actually pretty straightforward. The set of all scalar multiples of our value I is what makes up the imaginary numbers. Okay, so I is defined as a number z such that z is equal to some real number times I. So whenever you have like pi I, square root 3i, with I being on the outside, I guess I would rather say that as I square root 3. 5i, -2/3 I, all of those are in the set of imaginary numbers. Okay, so once we include a real number to that, right, like 2 plus 5i, we now have a complex number, right? So complex numbers are C. So we define that as Z such that Z equals A plus BI, A and B, both of those being real values. Okay, so complex numbers comprise our entire number system. So our entire number system are really just the complex numbers. Okay, and so what we mean by that is that if our imaginary part is 0 and all we're left is the real part, then we have a real number. In our complex numbers, if our real part is 0 and all we're left with is the imaginary part, then we have an imaginary number. Okay, and if we have both A and B being present, then it's a complex number. Okay, so complex numbers generate all of the real numbers, all of the imaginary, and it is itself, it's the complex number. So our actual number system that we use is the complex number system. So again, A is the real part. It comprises the real number system, which we call RE of Z, the real part of Z. So remember, Z is the number we're using. Z looks like A plus BI. So the real part of Z is that value A. Okay. B is the imaginary part, which we call IM of Z, or imaginary part of Z. The imaginary part of Z is that value of B that we have. Okay. So again, when A is 0, when the real part of Z is 0, we're left with an imaginary number. And when B equals 0, when the imaginary part of Z equals 0, all we have left is this value of A, the real part of 0, and we have a real number left over. Okay, So the other interesting thing about the complex numbers is that complex numbers come in pairs. We call these the complex conjugates. They're very, very similar to the radical conjugates that we used when we're trying to rationalize denominators. The A and B portions are the same in complex conjugates. However, the sign in the middle is different. So if I have a complex number, A plus BI, its complex conjugate is A minus BI. Okay, so again, if Z is the form A plus BI, its complex conjugate, which we signify with Z bar, is the exact same values of A and B. It's just that the imaginary part has a different sign. Okay, so this is taken from what we had before. We have the natural numbers, we have the integers, we have the rationals, and here we have the irrationals, but I've included into that the imaginary numbers, right? So if I take out this square and I'm left with this bigger rectangle missing this rectangle, that was the real numbers. So what we've talked about so far is including the imaginaries, and all of these combined is our complex numbers. Okay, so again, our imaginary number is I. Notice they don't have any real parts. It's a real number attached to an imaginary value, right? A scalar multiple is what we call this. So pi I, 1/3 I times square root 3. So whenever we have square roots, we generally write the I in front so that we don't confuse people and make them think that the I is inside of the square root sign. Okay, same thing with X. If X is a full number, we put it on the outside, right? Complex numbers have this form, right? The real part minus the imaginary part. The real part plus the imaginary part. So the complex conjugate, for instance, of 2 minus 3i would be 2 plus 3i. The complex conjugate of this would be 1/2 minus 4i. Okay. So now let's talk about how to do arithmetic on complex numbers. Okay, it's actually very straightforward. It's very similar to when we're doing math on binomials. So when we add or subtract two complex numbers, the real parts add together, the imaginary parts add together, right? When we multiply two complex numbers, we basically double distribute. We do the foiling, okay? So let's focus on the addition and subtraction. If this is one complex number and this is another complex number, whether or not I'm adding them or subtracting them, the two real parts will be added and subtracted together, and the two imaginary parts will be added and subtracted together. So I will add or subtract, depending on the sign that I'm using, A with C, the two real parts, and then I will add to that the B and the D plus or minus, depending on what's going on here, whether it's plus or minus. Okay. So if you notice, this is a real number. There's no imaginary values here. B plus D or B minus D is a real number, and it's attached to the I. So it's very, very easy to add or subtract these. You're just really combining like terms. Okay. So as I was saying before, if we want to multiply, we're really just going to double distribute. So I'm going to take A plus BI and distribute it across the second term here, right? The second complex value. So when we expand this, we can also think about this as either the double distribution, or we can go straight to the foiling property, which is A times C, A times DI, C times BI, and BI times DI. So that's B times D, and then the I is squared. And if we combine the imaginary parts together, we got the AC, ADI plus BC times I. Remember, I squared is -1, so this turns negative. So BD and AC are both real values, and I can add those together, and these two are imaginary values, so I can pull out the factor of I, or just think about it as adding those two things together, right? So I got AC minus BD. Remember, this changed signs because of the I squared. The AD and the BC are both of the imaginary parts, so I add them together. They're still an imaginary value, okay? So again, try not to memorize the formulas for these. We're just doing this in general very abstractly. This is pre-calculus. You guys have added and subtracted and multiplied and divided complex numbers before, so I'm not going to give you concrete examples. You can find those pretty much anywhere on the internet. It is in our textbook that we're using everywhere. So again, just think more about the process, the concept of what's going on, rather than trying to memorize the formula. But again, I'm really just foiling, or I'm distributing a plus bi across the c and the di. Okay. When we divide complex numbers, we run into the same problem that we were having when we were trying to divide by radicals, which is I don't understand what it means to divide by a radical number, right? I really don't understand what it means to divide by an imaginary or a complex number, right? Because that is even more out there to me, right? Again, I can divide something in half easily. I know what it means. I break it into 2 equal parts. I can even figure out what it means to divide something into 1.8 equal pieces, right? There's math for me to help me figure that out. We saw that in the last example, okay? However, dividing something into pi equal parts or square root of 2 equal parts, a lot less intuitive. I really don't understand what that means because the decimal form of square root of 2 doesn't stop. It keeps going on forever. So what does it even mean to look at one of the pieces that have a length of square root of 2? Okay, so if we extend that idea into the complex numbers, what does it mean to divide something by I? I'm going to divide something by the square root of -1. Okay, well, what about 5 plus 2/2 or 2/3 I? Now that's even more weird to me. I really don't understand what 2 plus 2/3 I looks like as a thing, right? So the goal then is to turn the denominator into something that we can work with, something that we do understand to divide by, something like 2, something like 12, something like 2.5, right? Some number that works for us. So what we're going to do is, again, I'm going to try to turn the divisor into a real number. So we're going to use the property of difference of squares with complex conjugates, okay? So same thing when we had rational expressions with the radicals, we use the radical conjugates. Here we're going to use the complex conjugate across the numerator and the denominator. Again, I'm multiplying times 1. I'm just trying to change the way my my numbers look. Okay, so if I want to take a plus bi divided by c plus di, okay, so take one complex number divided by another complex, or even a whole number, a regular number, right? Even if this was pi divided by 2 plus 3i, it still works. It really doesn't matter, okay? I'm going to take this number and I'm going to multiply top and bottom by the complex conjugate of my denominator. So I'm going to multiply top and bottom by c minus di. Okay, so this is going to turn into this. So again, I'm multiplying it by 1, right? Same thing on top and bottom. Means it's a 1. It's just going to change the way my thing looks. So again, this takes the form of a binomial, right? Yeah, there's no x terms, but it's still 2 separate terms separated by an addition and subtraction sign. So it's still going to utilize the difference of squares formula. That is, I'm going to square c, I'm going to square the di, and I'm going to subtract the 2. Okay. The numerator, I'm multiplying times one complex times another complex. So all I really did was go straight here, right? Copy and paste the formula, right? I could have done all the work, but I've already done all the work for what it means to multiply 2 complex numbers. So it looks like this. I went straight here and just, boom, copied the same thing, okay? Again, I'm applying the positives and negatives as needed, right? So there were some negatives going on here. So this is where they end up going from here, right? Because it's the di that's negative, so everything associated with the d should be changing signs. So here this was AC minus BD, but there's a D there, right? Here everything was positive. Here the D is negative, so here it goes from negative to plus, okay? Here there's a D as well, right? So that's going to make it a negative. The BC, as you see, stays positive, but the AD term's negative, so I just put it behind it and made it negative, okay? So again, very simple arithmetic. On the bottom is the difference of squares. I haven't done anything. I just took the C and I squared it. I took the DI and I squared it. So D squared, I squared. And it's a difference of squares, so there's a negative here. We know that I squared is really -1. So this is going to change to C squared plus D squared. Okay. that's really all I have to do from here. Okay, this formula works every time I want to divide, so you can plug it in as a formula. Again, the easier way to do that is think of it on a case-by-case basis and think of it conceptually. A, B, C, and D are all real values. The B and the D are attached to I, so them as a term are the imaginary parts. So C plus D is a real number. It's not complex, it's not imaginary. So now I have this thing here divided by a real value. So I can separate this into two separate parts if I need to. As such, where I have a real part now, right? AC minus BD over C squared plus D squared. Those are the real parts. This is the imaginary part, and it's also being divided by the C squared plus D squared. So now it's in imaginary form. This is basically my new A plus my new B, I. The real part and the imaginary part. Okay. So again, be careful. Okay, this is what I was talking about at the beginning. If you have the square root of negative A times the square root of negative B, you cannot throw those together under the same square root and be like, oh, now that it's a negative times a negative, it makes it positive, and there is no complex numbers or no imaginaries. It doesn't work like that. Okay, it's still going to be negative A times negative B. You need to pull out the imaginary part first. This should be I square root A, and this should be I square root B. Okay, so just be careful on that. Watch out for those. And again, if we were to simplify that, that would be square root AB negative, right? Because you got I times I on the outside at that point. Rather short video. Hope that was helpful. See you guys on the next one. Thank you.